And I did some research last year on beat profile and the performance. And basically, the whole picture, the whole project is on to try to evaluate different waveform, what kind of, we can achieve on the beat profile, on the strengths, and how the microstructure is going to look at. And very luckily, and we got a very good agreement between the profile and performance, which is strength, and also the microstructure. So first of all, I just briefly review what I did in the past. And basically, I used robotic the filler joint, which is I used the quarter-inch 6061 T6 base material. I used the ER5356 and the 1.2, which is 364 aluminum wire, and do the filler joint on both sides. And it's very interesting, I try to compare things. Basically, I choose the same warp speed, which gave us exactly the same productivity, same travel speed. But however, different mode gave me the different current and voltage. But if you look at last column, my heat input fairly close. I cannot do exactly the same, but very, very close. So afterwards, which is part one of my job, I did the measurement on my leg length, my side penetration, which is very critical for the filler joint, and my effect strut depth. And before I go further, because I did the comparison between the conventional CV and pulse mode and power mode. Power mode was developed by Lincoln Electric back to something like 12 years ago, but not so many guys really, investigate what, the benefit this mode can bring to the, manufacturing side. But basically power mode, instead of like the CV, you put a constant voltage, but they basically regulate your energy, your watt. So the whole process, you keep your voltage by the current constantly. And the benefit is that you got really, rapid adjustment when you got a fluctuation on your stick out. So basically give you very stable arc performance. And later on, I'm going to show, basically, you can see this is the conventional CC mode, this is CV, and the blue line is the power mode. And the following three slides show the macro of the CV mode and pulse mode and the power mode. I'm not sure you guys noticed the difference, but however, those slides, which is part one of my research, tells me, they're pretty much this, ballpark for the leg length. But however, if you look at the standard deviation, definitely you get the smallest one with the power mode. What that means. Also the same thing for your effective strut depth, as well as your side penetration. What that tells you, because that tells you this mode gives you the most repeatable and reliable process to join the part together. And further to my beat profile measurement, I did a bunch of extensive, basically, probably over close to 15,000 points to do my harness mapping, because basically I cut the whole T joint, do the quarter and half and the 3/4 cross section, and do all the harness mapping, quarter and 50% and 3/4. But you can see they repeat the same pattern, and power mode deliver the best high strength, and the smallest softening zone in the heat effect zone. Basically, I repeat from quarter to 50% to the 3/4. So very, very highly repeatable, I basically cut, 6 coupons for each joint, did those kind of hardness mapping. So very, very repeatable. Each those plot contain around 2,500 data points. And based on those, which is I present last year, then I did further why. I need to understand why. So this year we did lots of microstructure analysis on those. You can see that, even from different modes, this is CV, this is pulse, this is the power mode. You can see that definitely the power mode give you biggest equal X microstructure. And also, you can see that basically your temperature gradient changed from from the power mode to the pulse mode to the CV, but your cooling rate of that from CV to highest cooling rate to the pulse and to the power mode, which result in change of your equal X, the size of your equal X zone, which give you the highest strength. And also I did, just the 200 microns below my top of my plate, did the hardness line hardness scanning, and also shows, just give you one example, also shows, and I got the best performance, the last softening in my heat effect zone from my base metal. Very, very good agreement with those hardness mapping result. And this is the work, I referenced Professor Mayer's work from Norway, which is he published in the Active Metals back to 2004. Basically, if you look at those as the T6 condition, you got lots of very, very fine and even distributed, needle-shaped, precipitate in the aluminum, magnesium, silicon alloys. And during the welding, you got the heat treatment, kind of heat affect your base metal. Basically, temperature between the 250 to 48. And some small, very fine beta double primary is going to dissolve by the heat caused by the welding, and some will be get very coarse large beta double primary and large and very coarse beta primary, particles. Then after you, post-various heat treatment, they're going to, the fine precipitate will be show up again. And basically, this is publication by Professor Mears, and basically, you look at the, my analyze on the microstructure for pass 1 in the heat effect zone, you definitely can see lots of things happens. One, you can see that with my power mode, I definitely get really, really fine grain structure compared to my pulse mode and CV mode. This is at the same medication, but basically I took the same spot and take the snapshot on the zoom in the area. And I zoom in to my fusion zone, and with the columnar dendry and my equal X dendry, show the same very, very good agreement. And definitely, the power mode gave me very, very fine grain structure. And this is one thing. And also, if you look at those pictures, and in my CV mode, I also detect some liquefaction also with my pulse mode. And definitely, I didn't see any liquidation in my pulse mode near my fusion boundary. So basically, talking the crack resistivity, talking my strengths, definitely, fundamentally power mode gave lots of advantage over the conventional CV and pulse mode, which is kind of, in good agreement with my last year's research on the performance on my properties. And I got the same observation evidence with my past two, which is other side of my failure joint. Repeat the same result. So you can see that very big green size with my CV and pulse mode, but very fine green size with my power mode. And you see some liquidation, at the green boundary with my CV, a little bit with pulse mode, but almost nothing with my power mode. But same base metal, same filler metal, same, slightly. I noticed that the heat input for the power mode slightly low, but at least is within 5%, which is in the buck number, I repeat the same result with my fusion zone, which is my welding metal, both my columnar dendry and equal X dendry. And I further did some investigation used SEM, which I used the secondary SEM, electron beam. And you can see that with verify, I got some small liquidation cracking in my heat effect zone, and which I observed with my CV and pulse mode, but we didn't see those kind of liquidation, but however, we see very nice things. We observe some precipitate showing up in my heat effect zone close to my fusion boundary. So same thing with my, I did on my fusion zone microstructure SEM, which is not so much difference, but I can see very fine green size and also observe some precipitate, which is Mg2Si. And I did further, put on high medication, compare, in basically 200 micron from my fusion line, did 6-point observation optical microscope. This is 50 times, and I did 100 times, and I found basically repeat what I saw with low medication things, and you can see that you really get pretty big size of the green. This is 50 times, you can see, but power mode definitely give you lots of, talking the green size, green structure, power mode give you lots of advantage. So, and the last things I really want to know why a little bit further. So we did use the thermocoupling to measure the temperature in the heat effect zone. So basically, we put two thermocoupling attached underneath of my VAP, center plate, and which is something like within 1 millimeter from the center, and this is the parameter I use for my thermocycle measurement. Basically, I keep the same WPS as my previous one during my welding at the very beginning of this slide. So and it's very interesting that we found that power mode give you really, really low temperature distribution in the heat effect zone compared to my CV and pulse mode. So this is after welding, I break the T-joint just to verify my thermocouple location. And it's very, very interesting that even that, for some reason I put my thermocoupling really close, only 0.4 millimeter to my fusion line. There are two reasons. Basically, the origin the same. Why is so 0.4? Because I got the better side penetration for my power mode. That's why it's gave me a little bit this, closer than those one. Basically, they're at the same spot location, but I just can't, measure from my fusion boundary to my thermocoupling. Basically, you look at that, my thermocoupling fairly close to my fusion boundary. However, I got the lowest temperature distribution. So based on the current result and previous work, and I would like to conclude the following 4 points. One is that waveform technology has a significant influence on the beat profile of the failure joint in current research. And secondly is an improvement on the performance in both the minimum hardness and the width of the softening zone in heat effect zone is possible by using the power mode compared to the conventional CV and pulse mode, which is pretty much 95% people use CV and pulse mode, pulse mode right now. And third point is that the observed microstructures were in very good agreement with the micro hardness measurement and the width of the softening zone in the heat effect zone, which I showed you in previous slide. The last point is that the power mode has demonstrated the reduced width of the softening zone in heat effect zone and followed by the pulse mode and in comparison with the conventional CV mode. So maybe I present slightly faster, but lots of information. But I can spend lots of time explain each metographic image, but I believe you guys probably understand as good as I am.
Thank you, John.
Okay, any questions?